Thank you. So, yeah, my name is Widad Metrubi, and I come from the DLR Institute, which is the German Aerospace Center, which deals with many subjects, not only space, but also energy and transportation. And my work is going to be a little bit easier because of the introduction, which is, has been done by Tom. So I'm here to talk about the GIRD model that you saw in the previous presentation, but in general also about open source data and models and how can we use them in power grid modeling and analysis in a kind of a sustainable way. So the outline of my presentation is I'm going to give you a light motivation after the motivation that Tom just presented, and also introduce you to the GIRD project. And we use an open source database, which is the OpenStreetMap database, and I'm going to present today what OpenStreetMap is and which power data, which is the main topic, can we find in OpenStreetMap, and show you some results. So mainly the results are for Germany, for the GIRD model, but also some results for India concerning the data sets which are available. And I will finish by a conclusion and also some outlook to give you an idea how, for example, this data can be used in the case of India. So as Tom introduces for models, there is a problem because we have not only models which are lacking, but as you know, energy system modeling analysis is really heavily based on data. So you could have the best model ever, but as long as your data is incomplete or missing, you cannot go far. So this is particularly the case for power networks. I put transmission because that's the part I'm interested in today, but that's the same also for distribution. So data is a little bit even more complicated than models because it's in most cases it's under restrictive or very restrictive licenses, and sometimes even no clear license terms. So you can find some data, but you will have to look a lot to actually know, is this data available, can I use it, and in which terms I can use it. So many research institutes or many people refrain from using it as there is no clear license terms. If you have some data, sometimes it happens that you can find some data or get passed to you. You have little information available on how this data has been obtained. So what are the sources, what are the quality of these data sources, how has this data been aggregated, and also are there some simplifications or assumptions that led to this data set, and which are the simplifications and assumptions which are at the end very important for your modeling because your results will depend on those simplifications and assumptions. And in the case of transmission networks or power networks in general, there is also little information on how, for example, electrical properties have been calculated or even set. So at the end, you will have difficulty validating or comparing your results with other institutes or other people. And this is not really a good thing if you're trying actually to push for your analysis. And I come from a research institute. Sharing is, or discussing your results is a very important part. And this restriction on the data, it actually transfers itself to restriction in publication, in sharing with other colleagues or other institutes, and also it hinders cooperation as you're not allowed to do much with this data. In an institute itself or a company or in a group, the process of collecting data is in this sense endlessly repeated. So you move from actually looking at the results or the analysis into endlessly getting this data, cleaning it and using it. So that's a motivation actually to go for open source data. So what we decided to do, let's say, against that, is that we decided to apply for a project that has as a main task to actually produce an open source reference model for the European transmission network. And this is actually directed to scientific analysis, so a little bit more work is put into that. So we luckily got financed by the German Ministry of Education and Research, in the period of 2014 until the end of this year. And our motivation, like I said, is actually to have a whole project which is dedicated into providing robust and open data, and also the model that is actually used to obtain this data for the transmission network in Europe, for the research community, but which can be used by any other community. So our main objectives are to develop an open source model, to provide the community with not only the data of the transmission network, but also with the tools, with the models that we use to obtain this data, and to thoroughly and in details document this process, document the data, and also document the models we use to produce this data. So like I said, it's directed towards scientific analysis, but it can be used by any other community. So our vision in doing that is that if you have open data sources, if you use open data tools and models, software, and you document all that, you can actually reach that at the end. At the right side of the slide, you can see an example of the available data in OpenStreetMap that I'm going to introduce shortly for Europe, and those are what you see are transmission lines of the transmission network. So the SAGRID project, as I said, is financed by the German Ministry of Education and Research under an initiative of transmission of networks, power networks, which is called the Stromnetz. Okay, so what is OpenStreetMap? OpenStreetMap is the base we use for our data sets. So let me clarify at the beginning, what is a transmission network? Transmission network, as we see it, is substations which are connected to each other with transmission lines. So we need to build that transmission network. We need to build the connections between the substations, and therefore we use OpenStreetMap. So OpenStreetMap is your normal map like you are used to Google Map, but to the contrary to Google Map, you can actually download the data of OpenStreetMap and you can use it. So OpenStreetMap was founded in 2004 in the UK by Steve Cost, and it is to date the most extensive georeference data base in the world. And it includes not only power-related features, but it includes any feature you're interested in and you can map. So trees, houses, roadblocks, and as you can see, for example, here's an example of what you obtain if you look for New Delhi, for example. So the data that is actually in the back of this map is written in XML format, and it's really accessible. You can use it. You can, for example, take this picture, put it on a web page. You can route through the database, and you can do that under the Open Database license, which guarantees that this data is open, but you can also modify it. You can use it even commercially. So OpenStreetMap doesn't come only with the data, it comes also with some tools that you can use to actually process this data at your convenience. So how the data looks in OpenStreetMap and how can we use it? So data in OpenStreetMap is in 3 types. The first type is a node, which is representing any feature, for example, a tree, and this node is the only object which is actually georeferenced. So each node has a coordinate, and you can give these nodes tags or keywords. For example, if it's a tree, the keyword will be tree. If it's, I will show you how it's, for example, for the power system. And those nodes are actually the basis of every object in OpenStreetMap. As we cannot represent everything with a node, we need other more complex objects, and the next object is called the way, which is actually a collection of points which are connected to each other with lines. There are 2 types of ways: open ways, which could be, for example, road segments or transmission line segments, and there are closed way, which can be, for example, a footprint of a building. Also, those types have tags that tells you what is this object and also what are the features of this object. And again, if you want to represent things which are a bit more complicated than houses and trees, you need another object, which is called a relation, which gives you the possibility to actually put many objects together and relay them with their purpose. And relations are the most complicated object, and they contain nodes, ways, and also they can even contain other relations themselves. So how those objects are related, like I said, nodes are the basic element. You need nodes to make ways between 2 and 2000, and you need ways and nodes to make relations, and even relations can contain their own self. There are rules how to create those objects on the wiki of the OpenStreetMap, so it's not just done in a chaotic way, so that when you parse the data, actually you can use it in a significant way. So what does it mean for power and also for the transmission network? So a node, like I said, could be a power tower, and it has an ID, so you can recognize this node, you can call it, you can use that ID. It has a coordinate set, which is very important if you're simulating power networks, because you really need to know where this node is and what can you actually attach to it as generation or load or anything else, or even storage. And it has other stamps that you can use, for example, for statistics, when this node has been entered, or who's the user who entered this word, this node. And for ways, they represent, for example, power lines, and they have also IDs that can also relate them to the node that they contain. So ways have nodes, and those nodes have IDs, and then you can actually follow up from where the nodes are taken. They also have tags, so the power tag is the most important one if you're looking for power data, and here it tells us it's a line. So what's a relation? A relation in the case of a power data is actually the power circuit. So a relation is ideally two substations which are connected with each other with many line segments. It's a very important object, because if you want to construct a transmission network, you would like this work to be done for you. So you would like to have the route already there. But as we will see later, this is not an object which is present all the time in OpenStreetMap. In the case of Germany, we were lucky enough that this data type was really extensively used, but for other countries, this is not the case, because you need a kind of an expert mapper to actually do this assumption. But you can actually, there's a workaround that. So now we have, let's say, all the elements we need to construct our transmission network. And as I said, all this is in XML format. So if you go to the OpenStreetMap webpage, or if you download the data, it's going to look like this. So tags and keys, which tells you which object it is. It gives you some information which is relevant, for example, for power. What's the voltage? What's the number of cables? And so on. So now we have the data, and then we need to make a model out of it. So we pursue this kind of philosophy in the SciGrid model. We have three main blocks. So the first main block, as you can see, is the data, which is a very important part. So the raw data is downloaded from the OpenStreetMap. There are many ways to do that. You can download it for the whole planet, or you can download it for little regions. And then you do that by defining your geo-boundaries. Then you take this data, and you need to make sense of it. So in the case that you have really good representations of relations, then the job is not that hard. So you post-process this data, you clean it, then you put it in a relational database, because it's easy to handle, and then you run algorithms on it to actually derive the power network itself. And then, because of simplifications, we wanted that transmission network that is resulting is going to be abstracted, in the sense that we took away information which is not relevant. For example, how the lines actually, the actual path of the transmission lines is actually not important if you're doing a powerful simulation. Only the length is important, and this information is also there. So we kept this information, but we took away, let's say, the path of the transmission line. And then we define some other simplifications, like, for example, how we give the electrical properties to the transmission lines, like the resistance or the reactance. And at the end, we obtain, in the third block, the model itself, which is a package where you get the input data that we used. You get also the result, which are two tables, which contain the vertices and the edges. Vertices are the substations, and the vertices are the transmission lines, with all their characteristic, so their geocoordinates, their voltage levels, for example, and also other electrical data that you use to run a power flow simulation. And an important part is the documentation. So all that process was documented. There is a user guide. And there you can find information, how we did that, what are the simplifications. And the code itself is also available. And then you can, it's written in Python with SQL queries. And as Tom said, it's free and open. You can actually look in it. And if you don't like the way we do some things, you can also actually change it. We even pushed it to the point of also creating a little GUI for the people who were not familiar with using Python or relational databases. And at the end, even if you don't want to do any of this, you can just take the data as the CSV files. So what you do with the data when you have it, I will go through that. So there are some 3 examples that we use for that. So what are the results you expect from this project? The results are already there. The project is almost at the end. So we obtained the open source reference model, which actually includes the source code that you can download from the webpage, the SciGrid.de. You can also get the technical documentation, as I explained. And on top, you can get some converters to the power flow simulation software. For example, we saw PipeSA. So the PipeSA team actually wrote a converter from the SciGrid data to their software. And we have 2 other software converters, which are PipePower and MagPower, as they are first open source and also easy to obtain. We're in the process of validation and verification, which is never actually done. And we also pushed for scientific publications. So we published many papers on the subject, and we also organized this March an international conference where we had around 20 participants that we encouraged to use our data and also to validate or criticize the data set of SciGrid, and also to show results on their own. And that was actually a very interesting conference because we end up really talking about the modeling and the problems that everyone has with data and how to use it. In the following, I will show you some results for India. So the main, let's say, part that we're looking at is Germany and Europe. So here you can see an example, for example, for last month. So you can also update the data all the time because the data in OpenStreetMap is in a continuous updating process and actualization. So here are some numbers about how many of the substations we get for Germany, how many of the substations not only on the transmission network, but also you can do the same for the low and medium voltage. But those numbers for low and medium voltage are to be taken with reserve because they are harder to map than high voltage level transmission networks. We also get to find also power plants, which you can also obtain using the same code. So the model at the end is the 2 tables that you can see, which give you information about the latitude and longitude of the points, which are the substations, so their type, the voltage, the frequency, or the operator. And I left this intentionally empty because there is some missing data. So there is no way in saying that the data is perfect, but there are also ways you can use to complete this data that I'm going to talk about. So the same is done for the transmission lines. Transmission lines are, like I said, relating to vertices. So you find the 2 vertices at the table and the low. You can also find the voltage, some information about cables and wires, and also the operators and the length. So we did the same for India. So for India, because the code is not written for India, we get only the transmission substation and lines. Like I said, is to take a little bit with reserve. So that's really, really preliminary results. But you still can see that we obtain the same result. So we also have vertices and lines. And I was really surprised to find such amount of data because 2 years ago, we also wanted to check, is there some data for India? And the picture looked really empty. So there is some effort in India actually to put this data in the OpenStreetMap database. And you can see here some numbers of the substation and also the transmission lines which are available. So, like Tom said, the data is good, or the models are good, but what you do with them later is the most important part. And we try in a PhD work and also some master works to try to make sense of this data. So the first thing we did is we tried to characterize the German transmission network using the data sets that we got. And the first that come to mind is to compare it with the US data set, which is, let's say, the most famous data set available. And we try to do that, although the US data set is not really georeferenced, but we still could show that there are some properties which actually extend beyond the number of nodes and lines. And we did some really preliminary work in trying to look at clustering effects. The second project we completed is actually, like I told you, those relations are not present all the time, and so for Germany it was okay, but we intended to do it for Europe. So what we do, if we have the data, but we don't know the connections between the transmission substations. So we decided to use heuristic models and to take some assumptions. And through these heuristic assumptions, we could actually complete the data set for all Europe. And as the heuristic methods are really sensitive to the assumptions you take, we took great care also in documenting those assumptions, but this work is still, let's say, open to input from other fields. So you could see that that could be, for example, the case for India, because for India you have the raw data sets, but you don't have the connections, and that's could be an idea how to complete the data, for example, for India. A third work is that we just completed is that it's hard to compare data sets of a transmission network. So if you obtain a transmission network CSV file, for example, you will have a bunch of nodes and a bunch of lines, and you have your own data set or a partial data set, and you are asking yourself, okay, are they the same data set? Aren't they maybe just shifted by some degrees because an error, for example, in the georeferencing? So we faced this problem, and we wanted to create a tool for comparing transmission networks. So we did it on 3 levels. First, you can take your transmission network and you can also reproduce this characterization that we did in the beginning. So look at clustering coefficients, for example, look at betweenness centrality. And you can also do it in a geo-referenced way in the sense that you can put them next to each other and also try to use some buffers to try to see, are those two networks the same or not the same at all? And you can do it also in an electrical way in a sense that you can look, are they representing the same voltage levels, or is there a problem somewhere? And by doing this, you could also, for example, recognize errors in your own data sets. And we actually did this all in an open source way, and we put it into QGIS, so to give the opportunity to people who don't have a desktop GIS software to use it. Yeah. So to conclude, as we all know, we have new challenges in the energy sector, and this actually extends in a very acute way to transmission networks, and that makes them and their modeling a very important issue, which actually gets more acute because these data sets are not available. So we pursue the approach that if you base this on an open source philosophy for data, for models, you could achieve actually the goal of obtaining an open source model that you can actually begin to work with. And we see that this is not only applicable to Europe, it's also applicable to India, and it's a promising perspective as we saw data is available. So here are some ideas. How could we apply this to India? The first thing will be to characterize the data sets that are there, to clean them, correct them, and also to enhance them, and to encourage mapping, because OpenStreetMap is based on mapping and volunteer, and that can be actually done. And to adapt the algorithms and the tools that already exist for the special case of India and the special case of the Indian transmission network. And as you can see, there are already some initiatives. There's the mapping project for India, which is actually on the OpenStreetMap webpage. And for the idea we had for Germany or Europe, we actually created a web map that people can actually see for themselves what's missing, and they can actually go and put this information there. So it's our way to help people to map those elements. So thank you.
Thank you, Widit.
Yeah.
Right on time with that intimidating red blinking at you. I think we have time maybe to take a question, and then I think by the time we get all three speakers together, we'll make for good conversation. But do we have any questions?
Hi. How do you assess the degree of completeness of this data? So let's assume that for the German situation, there are 5% of lines missing, and you base a power flow calculation on that. You're in deep trouble. So how do you judge that?
Yeah, I mean, you're not in deep trouble because no one has a complete data set, actually. And how we base the completeness, we did the easiest thing is to calculate the distance, and we tried to really, in a brute force way, to compare with the TSO data, which is available. I mean, available between brackets because it's not really available. And yeah.
For India, how did you get the database?
How good it is? I mean, we cannot say because we don't have the original data. So we just got the data that is available in OpenStreetMap, and we just plotted it here. So how good is the data is dependent on the reference data set you have, which is actually the problem to obtain. How can you obtain this reference data to compare to? If you have the reference data, you can compare easily, but if you don't have it, you cannot compare. And actually, we had this discussion in this morning, so the worst open source data set is better than the best closed data set you can get because you don't have it. So what is your alternative? If you're simulating an energy system, you need, and in this detail, you need at least a data set to begin with. So it's not perfect, and it's open to change and actualization and enhancement, but that's the data set that's there.
And we are encouraging the TSOs to correct the data sets.
Yes. Yeah.
Can you extend your softwares to distribution side?
Our software, yes. We've taken more of a specialization into the optimal power flow, and Panda Power, which we'll hear about next, is more focused on distribution grids, I would say.